Hello, hello, and welcome to episode number 53 of the Wondrous Stuff Vodcast, broadcast live on Google Hangouts on air every weekend. It's a place you'll find news, information, and commentary on science, engineering, and technology from the past week and beyond, and anything else that interests us from inside our tiny little human brains. As always, my name's John Gardner, and to help me out on this journey to knowledge, let me introduce my colleagues, Richard Smith and Ross Davidson. Give it, say hello, chaps.
Hello, chaps.
Hello, chaps.
Jolly good. Jolly good. Right, we've got quite a packed show today. We've got topics from everybody, which makes a change. And
Yay.
yeah, oh yes, and Ross is on the new PC that was being built last week. Hey, it only took another 3 days.
Yeah.
So slightly optimistic to build it in 45 minutes. Anyway, so we're gonna start with you actually, Ross, and you're gonna talk to something about all the space junk up there and resurrecting satellites that are presumably out of operation.
Well, no, sort of. This is actually a story it's actually from a couple of years ago, but I was reading about it this week and I thought it was quite interesting. And this is a satellite that was actually launched between, well, it was a series of satellites launched between 1965 and 1976 called the Lincoln Experimental Satellites. And they were designed and built by the Lincoln Lab at MIT. Sponsored by the United States Air Force for testing various means of communication and that sort of thing. But these satellites had quite a few launch problems. The first two were supposed to be delivered to an orbit about 15,000 kilometers, and they failed at boost, and they end up at 2,800 kilometers in a circular orbit.
So presumably, were they supposed to be in the clock belt?
It was supposed to be a sort of elliptical orbit, but the boost stage left them in a circular orbit. And then the third and fourth one's supposed to be delivered to a geostationary orbit, which is even further out, I think. And again, there was a launch problem with that, so they didn't have much luck. Now, all these satellites did some work. There was a fifth and a sixth one. I don't know what happened to number 7. Oh no, yeah. Number 8 and 9 end up in geostationary. And basically, there was one of them was basically abandoned in 1967 because it just didn't return anything. So
how many was them in the whole array from the 60s to the 70s, 1976? How many were released?
There was 9, but I don't know anything about. Oh yeah, number 7 ran out of funding, so number 7 didn't actually get launched, so that was cancelled. Okay. So there was 9 of them originally. But anyway, they were sort of abandoned eventually. In 19, when was it? Oh yeah, that was another one. And then in 2013, what was interesting was an amateur radio astronomer in Cornwall was actually picking up signals and managed to pick up a signal from the first satellite, which had suddenly started broadcasting.
What, in the 60s? The one that was launched in the 60s?
The one that was launched first.
The very first one?
Yeah. And a radio astronomer basically picked up a signal from this satellite. Huh. Sort of like, how long? 48 years later. And basically, he managed to, all these satellites have, data. You can find out what it is, and he worked out that it was this LES-1 that had been launched in 1965. And basically, what they think was there was the wiring had sort of decayed, and eventually just started working after 40 odd years. Now, this wasn't actually the first.
To a point of decayed. Back into operation. That's
basically, yeah.
But not. Well, okay, right.
Which seems counterintuitive.
It is a bit, yeah.
But it's happened. It's happened again as well. There was another one, one called AMSAT Oscar 7, which was an amateur radio satellite constructed by AMSAT NA, North America, I assume, and that was launched in 1974. And that was actually operational until a battery failure in 1981. And then 21 years later, it started broadcasting again. And basically what they think has happened is, again, the battery sort of shorted out and just broke.
So none
but
of these
then,
have got solar panels on. These are all
this
battery operated.
this one does.
Ah, right, okay.
Yeah.
Well,
So
I
this
can
one
understand that then.
has power from its solar panels.
Yeah, right, okay.
The first one, I don't think ever actually sort of powered up, and it sort of just started transmitting. But with all this technology, like I say, it's from the 60s, so it's not sort of like modern, microchips and stuff like that. It'll be very sort of.
So it's probably going to be something like it won't. It might not even be silicon transistors. It might be germanium transistors.
Yeah, exactly. Yeah, I suspect so.
Wow. That's doubly impressive.
So the AMSAT one, they basically think again. They think the cause of the outage was a short circuit in the battery, and then eventually that, because it will sort of degrade, and eventually that short circuit went away, and the solar panels kicked in again. And there's actually there's a video of one of them where you can basically hear the radio signal, and they think it's rotating every sort of 4 times a minute or something, because of the way the signal sort of goes up and down.
So what you're getting is like what you were getting in Binary Star, where
yeah, basically,
sort of, yeah.
Right. So they can work out how fast it's rotating by analysing the signal.
So I mean, we've always known that there's a heck of a lot of space junk up there now, but whilst it's really quite neat that these have all started working again. There's nothing really we can do with them, though, is there?
No, I don't think so. No, I mean they're transmitting, but I don't think they're transmitting anything useful. So I think
it'll just be like a call sign.
Yeah, there's a signal coming from it.
Yeah.
But the actual electronics are a bit knackered. But just the fact that it's been up there that long going round didn't make it to its original orbit in the first place. Just again, talking about space junk, just gives you an idea of anything that goes up there, unless it's sort of deliberately decommissioned, like you like to do with the bigger things like space station like Mir and stuff like that. These smaller satellites, they'll just go round and round, and eventually they'll come down, because ones this old probably won't have much to keep them in orbit.
See, the one thing that really just confuses me is that I can kind of understand if you've got solar panels out there, because you're not going to be reliant on some sort of cell to keep the power. But they've got batteries and start working again. I don't understand how that can be.
What it says is that it has been suggested that after 46 years the batteries have failed in a manner that allows them to carry charge directly through the transmitter on 237 megahertz, allowing it to start up when it's in sunlight. So I think effectively it's working like a solar panel, where the sunlight is causing it to power up.
Right. Okay. Yeah. That's a strange one. I just don't. I mean, I know enough about basic battery cell technology to be confused by that description. But yeah, I guess it could. I mean, I suppose it's just over that time you would naturally assume that unless you've got some of the newer battery technologies like they're releasing now, where you can store a charge for a year or so, it would just dissipate.
This says unusually for communication satellites, they were powered by MHWRTGs rather than solar panels. Now, what's an MHWRTG?
That's the next question.
It's a multi-hundred-watt radioisotope thermoelectric generator.
So it's nuclear.
So it's a little thermoelectric generator. Plutonium.
Ooh, well, there you go. There you go. That's fair enough. That makes entirely clear now, because that's obviously the half-life of that is going to be.
Yeah.
Yeah. Oh, right. Okay. Phew.
It's nuclear.
So they didn't run out of charge then, they just stopped operating.
Basically, I think the battery, because it must power the battery and then the battery.
Well, presumably it would need that to filter the signal.
Yeah, to like
You'd have to
modulate,
have a
yeah.
smooth signal
Yeah,
to operate the
yeah.
electronics. So presumably the battery is just being used as an interim charge mechanism, or there'll be some sort of transformer of some sort. So I can understand now. Right,
That
that's
makes
okay.
more sense, doesn't it?
That's that little phrase there that you said, that makes it all possible.
MHWRTG.
That one. No, the fact that you doggone it, you know what I mean.
Plutonium.
Plutonium.
Way aye, man. Anyway, that's good. It's interesting. It's interesting to know, but there's not a great deal we can do about it, is it? I mean, it's still, other than we know that 1960s technology is probably quite reliable, really.
I mean, it's one of these things, I suppose, with stuff that's in space. Obviously, it's a vacuum. They're not going to rust.
I wonder. I wonder if there's if it's now operating. I wonder if there's any possibility that, I mean, bearing in mind all the people who originally launched these things will probably be long gone. I mean, I don't mean in the death sense, but possibly that also. But they'll certainly not be working for MIT.
No.
And I just wonder if there's any possible way they could send signal up there to move out of orbit and crash into the sea or something, so they can clear the skies.
I don't know. I mean, these things, they'll be that small that hold on, I'll find a picture. There's a picture. Let's get a picture up.
They're all right with the stuff where they know where it is. It's the stuff where they don't know where it is.
Yeah, exactly. Yeah. And I mean, this is the thing. If you've got something up there and it's not transmitting, how do you detect where it is? You know, I don't know. Can you get radar to look at satellites? Would that work? Or do they track satellites via their transmissions? I assume they do.
You can track forward as long as it's as long as it's somewhat predictable. But yeah, I guess once you start going out of a predictable pattern, then you lose track, don't you?
Yeah. But things that are this size, they'll just burn up in the atmosphere. There'll be nothing will land.
Well, it's just whether you collide on your way out. That's the issue, isn't it?
Whether it hits another satellite.
Yeah, or something on its way out of the, leaving Earth.
So actually, just put that back up, Ross, and I'll just highlight on that.
Oh.
So that there, you can't. Sorry, I'll move away from my microphone. That's bad technique. You can see these solar panels around here as well. These are all little photovoltaics, aren't they?
Well, that's what they look like. But
what do you assume they would be?
Yeah, they did say it didn't use solar panels, but that does look like solar panels, doesn't it?
Yeah. God, just think how much they would have cost originally, and how much they would have cost now because they're made in China.
Yeah.
Wow, incredible. Right, excellent, good. That's a nice little story, actually. I like to hear about old technology doing good or coming back to life. That's great. Okay. Well, on from space to genetics, I believe. Genetically modifying the fight against disease. Go on there. Tell me about it there, Richard.
So there's two related stories on this.
Cool.
So first of all, white blood cells, they fight things that shouldn't be in the body. They're part of the immune system. They're naturally equipped to eliminate infected cells especially, but some diseased cells too. They're not very good at identifying and killing cancer cells. So this is an effort to try and make them better at that. So you can get a virus, which is completely harmless. You can introduce two genes with it. The first gene makes it easier to grow the cells that you want to grow to kill the cancer cells, that helps it in the laboratory setting to multiply. And then the second one is to recognize and attack the cancer cells.
So is this attaching a virus, essentially attaching a virus to a cancer cell, so that the white blood cells attack the virus and hence the cancer?
This is gene therapy, so this is putting gene inside of a. So basically, the virus is the vector. So you put them inside the virus, and then horizontal gene transmission into the host. So it sounds sort of dodgy, but then when we do bone marrow transplants and things like that, there's gene transfer there as well. So it's not really novel in that sense. So this is actually being done by the National Institute for Health and Research Biomedicine, and that's British.
Wow.
So it's happening in the UK. The treatment's called CAR T-cell. It takes only 2 weeks to produce the treatment. And at the moment when they're trying it out, they're injecting them directly into the tumour. But so this is for head and neck treatments, because they tend to kill people by the tumours and staying in the same place. Other forms of cancer tend to kill people with mitosis, so the cancer leaving the original site and getting into the lymph nodes and what have you. But head and neck cancers tend to be very tumorous, and normally it's the tumours that kill you. So it's for that.
Because it's the head and neck cancers is they start pushing against things, don't they?
Yeah.
And that's so, especially in the neck, if it pushes against the spinal cord, then that's how you become.
But also they'll spread locally as well. So okay, you're not at risk of it going through your whole body as much, but obviously you don't want a cancer spreading through your brain, because it's going to destroy whatever it comes across, isn't it? It's going to displace healthy tissue. So that's what's going on research-wise. But actually, 2 months ago, it was used in anger. There was a child called Lila Richards who had a highly aggressive form of acute lymphoblastic leukemia, which is basically a fatal terminal diagnosis. So she was 1 at the time. It was only a couple of months ago, so she's probably still 1 now. Back in October, and basically the treatment, the T-cells treatment, which is not exactly the same as this CAR T-cell mechanism, but using T-cells with genetically engineered properties. Basically, I think 25% of children with aggressive forms of this survive, but in her case, she'd already received the terminal diagnosis for the tried aggressive chemotherapy and stuff like that, and the outlook was bleak, and they'd only tested it on mice, so they had to approach the get an emergency ethics committee, and basically because she had no other
she had no hope of surviving otherwise.
She just basically had no likelihood of survival, so they went for it, and she's still alive. She's been given the all clear.
All clear, really?
Yeah.
Within that small space of time.
Yep. So she's actually home now because she's
Blimey.
And that's a good thing about it. If it does work,
works straight away.
This is the first human, but if it does work, then you're fine, because basically it's trapped the cancer. It's not like chemotherapy and radiotherapy and stuff like that where there's massive side effects.
Because it's all using the body's own immune system.
Exactly.
It's got nothing to reject.
Yeah, exactly.
Wow.
She did have to have a second. So she had a bone marrow transplant as part of the chemotherapy, and then she did unfortunately have to have a second bone marrow transplant.
I presume that's the kind of clear everything out again and start fresh.
Exactly. But also to the fact that our immune system had been totally wiped out by the treatment. So and our blood all had to be replaced as well. But within a month, so that was the reason that she had to have that. But within a month, she was well enough to go home. So good news story, and they're going to try clinical trials of this second one early 2016.
So now they've had it. So they've done this because there was no other hope for this girl, and they got an emergency ethics committee, like you said, sort of a pass, as it were. But now, presumably, they still have to go through the normal trials, and they still have to do it properly to get it, certified.
Well, they've said you can't extrapolate from that because it's one person. You could have an early success and then a string of failures, couldn't you?
Yeah.
But it's promising. There's obviously a lot of research going into it. The first set of research I talked about there is a novel way to do it, and they're hopeful about that. So they've got mice trials up and running with that. But yeah, I mean, there's 10 10 children a year get this condition that she had, get this disease that she had. So with those people, you kind of may as well, in a sense, because also they have a high degree of returning. So the treatments don't, the radiotherapy and chemotherapy don't seem to work fully. They just put you into remission. So if this is not only effective but permanent, then it's a massive deal, isn't it?
Absolutely, yeah. That could, that could be one of the breakthroughs that were, because obviously there's various cancer research teams doing all sorts of things all the time, and I guess they're looking for an inroad.
Yeah. Well, that's what you'd like to think when you do one of these stories, is that maybe not so much when we do supervolcanoes, but maybe one of these stories that you look back in 15 years and you think that was actually the moment. That would be nice. Not that was the moment that we speculated Yellowstone would really go up, and it really did.
But, I mean, there's certain things that we can't control. Supervolcanoes, really, it'll either happen or it won't happen.
Yeah.
But I guess this stuff like this again, it brings back the old argument of us playing God and stuff. But then I don't know. It's.
I think. Do you not think that's like largely a misunderstanding though? Because, like I said in this one, we already do that. So if you're a purist and you're a fundamentalist or whatever, and you're against bone marrow transplant, then I can see obviously you would be against this for consistency. But what I don't get is there seems to be a large number of people who are against this, but completely fine with, I don't know, it being used on crops, which you then eat. But even those people are fine with that, but like intensively bred crops that against that, and they're fine with intensively. I don't get why they're drawing this hard line between.
Well, we've talked about this before. We've talked about the how people are against GM modified crops, but then they're fine eating carrots, even though that effectively that's been manipulated somewhere down the line. Carrots weren't orange. We've talked about this before. And anything like that, if you're splicing two different plants together, if you're doing manipulation, whether it's sort of like a physical sort of level that you can see with your own eyes, or you need some electron microscope or whatever, you're still doing a manipulation.
Yeah.
I
mean, I can see the concerns in that, like, you might release a super pest into the environment and stuff like that that's completely resistant to this, that, and the other. But that's the same as if you breed it. You know what I mean? You could breed that into something in just the same fashion. So yes,
I think the thoughts on that is if you were breeding it, you'd probably notice whatever you're doing getting slightly aggressive slower.
Yeah.
Genetically modifying, you could do it in a generation sort of thing.
I'm not sure how true that even would be though, because would you not? Sometimes the risk you would have thought wouldn't be noticed until the population of it was huge and it was within an ecosystem and interacting with all the things in that system. So you would never really be able to model it until you released it anyway.
Yeah. And also that is not an argument to not do something. What it is an argument is to say is that you must follow normal experimental procedures. You must follow normal test procedures, proper regimented tests, and that's the only way you're gonna. It's not a way of, an excuse not to do all that stuff. That stuff still has to be done.
To be honest, I would be, if I was going to be more concerned about one or the other, because I know there is some arguments about tail risks in terms of GM crops and stuff like that, which I can't quite get my head around, but I'm sure there's something in that. But in terms of this kind of stuff, where it's on an individual and it's their risk to take or their parents' risk to take, and the back's against the wall anyway, it seems to me...
Not really a risk when it's a last chance sort of thing, is it? The risk goes out the window, doesn't it?
Mm-hmm.
Yeah. It might kill her. Well, if that's the worst thing can happen, that's what's going to happen anyway, so...
Yeah, so you might... The possibilities are it might hasten the demise of the person. It might give them a little bit more life, or it might, as what looks in this case, completely cure them.
Well, they said the doctors have actually said who did it that you'll have to give it a year.
Yeah.
But it's promising signs, early signs anyway.
And again, that given them a year is probably exactly what they would do under chemo or anything.
But the thing is, I mean, if this little girl was terminal and she's now at home, that in itself is, they've already, succeeded in something there. If it then turns out within a year she, goes back and ends up dying, well,
I think
had an extra
got
year
home for Christmas.
in terms of the treatment, though, it's promising regardless what happens to her in a sense, because they've had some early success. They've just got to, if it goes wrong, they've just got to identify why it went wrong and then make it more aggressive, less aggressive, whatever it is. Make more of this, less of this. You've just got to then refine the process, haven't you? But I suppose the researchers, in a way, will be glad that they've, I guess this relaxes all the ethical decisions having a situation like this, doesn't it? It allows you to go live on a human, and you've just completely skipped out primates and dogs, and you've skipped out the 10 years of testing, haven't you?
But it's something that we've discussed before, and I think you've said it, Richard. Is basically the only way you absolutely know what's going to work on a human is to test it on a human.
Yeah.
There are lots of things you can do. There are computer models. There are testing on animals, but if you want to know how it affects a human, it has to be done on a human.
Well, a bit like
some point.
A bit like we're saying about the genetic difference between animals last week. That percentage difference obviously makes a huge difference in the way diseases develop.
Because it was just to correct what Chris said, it was about 95%, wasn't it?
Yeah.
The difference between
comparing different things. Well, the first thing to say is that number has the
changed.
The gap has increased, but also it's two different figures. There's the amount of overall genetic shift, and there's also the mitochondrial DNA, which is kind of like the bit that's more important in terms of what we were discussing. So you obviously want to compare apples with apples.
So sorry, Chris, but that's the way it is. Facts are facts, man. Right. Okay. Excellent. So is that all of your topic, or
that was the two stories? So one about the research and one about the fact that
it worked. It all appears to work.
The research one was the virus introduced one. The other one was just T cells in general. But it just seems as though very recently, last 3 months, we've made a great deal of progress on it. So it's good.
Excellent.
So just one final question, just to go back to the sort of original part of the story. Is there anything the body does naturally to fight cancer? Or is it something the body just can't handle at all?
It's just not very good at identifying cancer cells. And cancers, when they're not caused by, there's a couple that are caused by viruses, not very many. So you've got a chance at that stage of your immune system fighting that virus. But once you've got cancer, as in a copying error, your body's not really evolved to identify that. So it doesn't see the cancer. It sees the cancer cells as native cells to the body. It doesn't see them as outsiders, so it does nothing about them.
And is there other research projects like this where basically what you're saying is we are artificially saying here's a neon sign, this is a cancer cell, you need to attack this? That's what, because effectively that's what we're doing. We're getting the normal white blood cells to go here.
To identify a difference. Yeah.
I guess
I'll learn a bit more about exactly how they manage that, especially with the gene technique. It just seems, but I guess that's the thing they'll be wanting to refine is the reliable, that the virus never then, they're seeing a harmless virus, but the virus then never goes rampant and carries on attacking healthy cells. You obviously have to watch for that. But that's the same as any treatment. Chemotherapy and radiotherapy damage normal cells, which is why people lose their hair and all sorts of other ghastly side effects. It's because it isn't that targeted. So
I mean, it is fairly horrific. I think what people don't realize is the actual treatment is also very horrific.
The treatment is a scattergun, essentially. That
sledgehammer to crack a nut type of thing.
It happens to get some of the hostiles, but the collateral damage is huge. Whereas if it can get it to the stage where it's just attacking the cancer cells, then not only is it a more effective treatment, but also if the side effects are greatly reduced. And that's the holy grail, isn't it, of effective disease treatment.
So one last question is this you probably don't know this, but will this treat other cancers as well? Is this method reproducible?
The virus one is because it's not very mobile. And obviously you'd have some issues around making it more mobile, and how would you control it and how would you target it? But because head and neck cancers aren't mobile, and if you've got a single tumor, you can just inject direct into the tumor. It would be more challenging with a cancer that's everywhere in the body, but I'm sure that they'll advance it.
Excellent! Wow, a good news story. That's brilliant. It's just what you need before Christmas, isn't it? Right. Well, actually, we're dead on track. This is great. This is the first time in weeks that we've actually had A, 3 stories, and B, we've been hitting the targets of time. Brilliant. Anyway, I'll get on with mine so I don't go over time. I'm going to talk about antibiotics. Now, there's been obviously a lot of talk about antibiotics over the last few years. Specifically, there was a story back in November from China saying that essentially we're getting to the stage now where there's more and more antibiotics becoming resistant to the drugs. So there's bacteria becoming resistant to the drugs. So what I thought I'd do is I cover those stories, but I'd do a little 101 on what are antibiotics. Now, antibiotics are a set of drugs called antimicrobials. Their sole purpose is to treat bacterial infections. This is the first misnomer, is that they won't do anything else. They're just for bacteria. So if you go to your doctor with a flu or cold, it'll do nothing for viral infections.
Or even an infection that's not caused by bacteria.
It'll not do anything unless it's bacteria.
But or an infection that's caused by bacteria, the bacteria has long since died. It's not going to help you get rid of the symptoms.
No, that's it. And this is one of the problems. I'll come back to this later. So what do we know? What do we know about antibiotics? Well, we'll know about Alexander Fleming. He invented penicillin, and that was the antibiotic. It changed medicine. It changed the whole of medicine at that point. And that was back in 1928. But there were a few antimicrobials before then. There was one in 1907 called arsphenamine, and that was a syphilis drug. Syphilis that cured syphilis, but there was a few before then, but they were very specific. I think penicillin was the one that it cured tuberculosis. It cured all sorts of things like that. So that was the main one that changed the face of medicine. The big problem with all our antibiotics is that all of the ones that are in use today, currently being prescribed by doctors and vets, actually, they were all discovered prior to the mid-1980s. In fact, the last one was discovered in 1987. So the problem is that it's about 30 years old now. And obviously, the more you use antibiotics, the more the variations of bacteria come into contact with a limited number of antibiotics. So the more this happens, they evolve methods to resist the drugs, essentially. And we now know that antibiotics have been overprescribed by doctors and veterinary surgeons for many, many years now. And this is a major cause. And we're going back to what we said before, whereas you'll go to your doctor and go, I feel awful, doctor, can I have some antibiotics? And they might even say that in a Geordie accent as well. Well, if it's not a bacterial infection, there's absolutely no point in you getting anything for that, because it ain't going to do a damn thing. It might be act as some weird placebo, but that nothing medical will change that. Now, back in November, this is the story I alluded to before. China reported a major increase in resistance in a particular type of antibiotic called colistin. Now, colistin is an old antibiotic, but it was always used as the last resort antibiotic. It was the one where all of the other stuff was tried. It hasn't worked. We'll whack colistin in. It whacked everything with a big hammer, and normally cleared the infection away. But they found that the resistance mechanism in this is carried on a mobile piece of DNA called a plasmid, and they designate this as MCR1. Now, they found that there was a major increase in this in resistance to this MCR1. That was back in November. I remember that coming on the news. It's quite a big story, but I don't think anybody understood the implications other than, oh, it's a bad thing. In the start of this month, Denmark did some research and found that this MCR1 plasmid was present in at least one human that they tested in this research project, and they found it in 5 food samples. The implication being that this plasmid with the antibiotic resistance is starting to travel the world, and obviously that is really bad for us, because we at the moment we've got nothing to help this. Well, at least I thought not. Doing a bit more research, something that I found that I don't think I'd heard of before earlier this year, back in January, February of 2015, and I don't think we discussed this, but there was another bacteria. There was another antibiotic discovered.
We did discuss it. I did it as a topic.
Did you do that?
Yeah.
Was this Teixobactin?
Yeah, a second generation of antibiotics.
And did you see this is? I'm starting to forget things now. Did you cover how it was actually, what the uniqueness was of how it was actually created?
Not sure. I just discussed how it basically would give us like a complete mixture. So then we could do all the antibiotics, the generation that we currently have, and then if they were to fail, we'd have these as a complete new suite of antibiotics.
Well, okay. So this Teixobactin that Richard obviously discussed about earlier this year, it covers what penicillin would do. So it copes with tuberculosis, it copes with septicemia, it copes with C. diff, many of the common infections. But it's not so much the antibiotic. This particular antibiotic. This is not the important bit. The important bit is how they discover this and how they manage to refine this. It's a new process, and it uses soil, because the scientists have long known that soil has the potential to harbour many new antibiotics because of the way it fights off microbes. The problem that they've always had is it's really been hard to grow them in labs, and 99% of these new microbes in the soil wouldn't grow on a standard agar Petri dish plate. So what they found is Northeastern University in Boston have found this thing invented this thing called an isolation chip. Now the documents I was originally reading on this it just said a chip, and I was naturally thinking it was an electronic chip, an IC or something, integrated circuit, but it's not. I'll show you what this is.
It's a potato chip. It is, isn't it?
No, it's not a potato chip.
It's wrapped in newspaper.
This is what it is, right? Okay. So here is this grid thing is the actual isolation chip, and it's essentially a diffusion chamber. So if you look at it on the side down here, let me just go into here, this bit here. This diffusion chamber is sandwiched between two bits. Between these two breathable materials with pores, and they're big enough to let nutrients in and waste out, but small enough to contain the bacteria. And if you see each of these individual little dents in here, there's a microbe on there. And what they've found is this this isolation chip. It's just a hard piece of plastic with 192 little wells, and that's those little white wells. The device allows them now to grow, get this, 30,000% more bacterial colonies than they could on just an agar plate. And essentially, it's going to change the whole way now, because they've got all that extra chance of getting all those new bacteria.
Cultivate a lot more stuff, basically.
Yeah. So apologies to Richard for jumping all over his topic that he
No,
did.
that's all right. Well, no, it's a different aspect to it.
So it's the method now. Now they've got the method, and now they've come across this invented this sort of piece of apparatus. They reckon that it's going to open, the floodgates for a lot more antibiotics, and looks like we need them pretty damn quick.
Well, what you didn't see in the introduction, which I think is important to mention as well, is on the livestock front. It's not just veterinarians. It's the actual commercial companies behind the meat industry have access to these as well, and they just use them carte blanche because it's easier to prevent bacterial infections from their point of view than it is to treat them. So they don't wait for an infection to wipe out £1 million worth of livestock. They just keep them pumped full of this all the time. And obviously it's a bit of game theory, really, isn't it? Because that doesn't do any of the other growers favours, because then when something does hit, it comes in and wipes everyone out. But because it's commercially driven, they only care about their own stuff. So I think that's a challenge that we have on our hands. I suppose you could deal with it through legislation, but apparently the people in the know are saying that, people get a lot of hyped up about, hand washers even got it in now, and which is probably a little bit worrying, but compared to the fact that we're entire food supply with billions and billions of animals, and they're just using it all the time, that's where you're going to get resistant strains coming from, because it's just going to be, it's a breeding ground for it, isn't it?
Mm.
No, you're right. Absolutely, you're right. It's we've got to pull back on stuff like that, but it's a real problem.
Well, is it like the hidden argument behind vegetarianism that doesn't really ever get made as well? That if you do talk about tail risks, then going vegetarian might prevent a massive die-off of animals or even people in the future, by the fact if we reduce our dependency and demand on livestock, we maybe don't need to use such intensive methods. And then if we don't need to use such intensive methods and keep animals in such close quarters, then we also don't need to use because that's the thing as well, is that it's the animals that are in very close quarters in intensive farming that they use these techniques. Animals are out in the field. They don't, if they're kept like wild animals, you don't really see these bacterial infections in the same way. It's the fact that you try and throw 1,000 chickens in a barn and you're going to see more bacteria and more bacteria spreading quickly. It's about farming methods, isn't it? It's just trying to make it more intensive.
Yeah, which is again, we've discussed this before. It's whether you can ramp up an already largely inefficient method of farming and to feed the population of the world, or you're going to have to look for something else.
Yeah.
That's one of the main things. Right. Well, that is all we have time for today. But we slightly hopeful end there. We have some possibilities of some new bacteria. New bacterias, no. I hope not new bacteria. Super bacterias. They will kill your cat. And possibly other things. I'm just gibbering now. So anyway, that's all we have time for tonight. We hope you enjoyed it. As always, we're looking for feedback. What I like to say is I've put this on the blog page on wonderofstuff.com, but we are now live on the Pure Connect service that Pure operate for all of their digital devices. This is the Wonder of Stuff page on the Pure Connect site. You can get the download of the audio version of this, which obviously for most of the things it'll be fine when we're just rabbiting on. Obviously you won't get the wonderful, hugely artistically created images that we use to highlight things, but you'll still get us talking rubbish. And probably next week I'm going to try and get us on iTunes, so that should be good as well. we have noticed a lot of traffic starting to come up from these things, and the fact that Richard is now being our official librarian is now making everything look better in terms of the naming of all of our archive of podcasts. So hopefully tell your friends if you've enjoyed it. If you haven't enjoyed it, tell your friends.
Tell us.
Just tell us.
Tell
And
your
also
friends.
tell your friends as well.
I watched this podcast last night and it was awful. What was it? It was The Wondrous Stuff. You can access it via the radio website. Oh.
Are we going to mention the launch tomorrow, by the way?
Oh yes, absolutely. Yes. So we've got the Britain has an cosmonaut. Tim Peake is getting launched into space from the Kazakhstan cosmonauty dromy thing. What's it? What's it called? What's the official? The Baikonur
or something.
Baikonur cosmonauty.
It's in Kazakhstan.
It's in Kazakhstan.
It sounds like it's made up, doesn't it?
So so he's.
It's where Yuri Gagarin got blasted off from, isn't it?
It is. Right. It's where all of them go from. It's
Borat involved.
It's what?
Probably, yeah.
Borat.
Borat. So he's going. He's representing the European Space Agency, and because it's the only way they can get to the International Space Station, because the Americans haven't got anything at the moment, really. They're going to use the nice, efficient but very old technology from the former Soviet bloc, and he's the second astronaut or cosmonaut we've had. There was Helen Sharman.
Yeah, I was going to say, yeah. I don't know if we've had any more. That's a good point.
We're not very big on the old. The UK Space Agency is in a porta cabin just outside of Leicester, and
there's been 7. There you go.
Has there?
Helen Sharman in 1991, Michael Foale.
Oh, of course, yeah. Of course.
Mark Shuttleworth. He was a comedian.
Mark Shuttleworth, isn't he the guy who started up Canonical?
South African / British.
Yeah, he was the one who sold Thought to VeriSign and runs Canonical, who make Ubuntu.
Yeah. Piers Sellers, Nicholas Patrick, Richard Garriott, and Gregory Johnson.
So I take, but this is the first person the first British man who's been to the International Space Station.
That's probably. I don't know. Richard Garriott went to the ISS.
Yeah, but he was a naturalized American though, wasn't he?
Self-funded, yeah.
Anyway,
it's happening
on Tuesday. It's the 15th.
Is it first thing in the morning? Is it?
Yeah, it's the takeoff is morning time, around 10ish, I think, and by about 7, which is 7 UTC. Is the time when they're going to be connecting with the space station.
Yeah.
It's live on BBC One.
Oh, yes, you mentioned that, didn't you? Yeah.
So there you go. Watch it. I think, yes, they're doing a Stargazing Live special. So I think Dara and Mr. Cox are doing the...
Excellent. They've got the launch on BBC One as well.
Yeah, that's the full thing. Yeah. Which is interesting because nobody seems to have cared since 1969. So now we're all really pleased that we've got somebody from Britain up there.
Yeah.
Excellent. So that's about it. So enjoy yourselves, everybody, and see us for episode 54 next week. It'll be the first one. It'll be the last one. It'll be the last one before Christmas. And so no doubt I'll have time to remind you for the Royal Institution Christmas lectures, like I did last year, and that's a space-related one. It's about living in space.
Oh, cool.
So that should be quite good. Okay, everybody, thank you very much for watching, stroke listening if you're on the podcast, and we'll see you next time. Bye bye now.
Bye bye.